Across the cosmos, breathtaking light shows adorn the skies of countless worlds. These celestial ballets, known as auroras, are more than just stunning visual spectacles. They are profound indicators of a planet's magnetic field, atmosphere, and its dynamic interaction with its star's energetic particles. Understanding them unveils secrets of planetary evolution and habitability. On Earth, we call them the northern and southern lights, the aurora borealis and aurora australis respectively. For millennia, these shimmering curtains of light have captivated humanity, inspiring myths, legends, and a deep sense of wonder, appearing as ethereal dancers in the polar night. The science behind Earth's auroras begins with the Sun. Our star constantly emits a stream of charged particles called the solar wind, traveling outward at incredible speeds. This invisible river of plasma carries with it fragments of the Sun's magnetic field, influencing everything in its path, including our own planet. Earth possesses a powerful global magnetic field, generated by the convective motion of molten iron in its core. This invisible shield, called the magnetosphere, extends far into space, protecting our planet from the harsh bombardment of the solar wind, deflecting most of these incoming charged particles away. However, the magnetosphere isn't impenetrable. At its poles, the magnetic field lines curve inward, acting like funnels. Here, some of the charged particles from the solar wind can penetrate Earth's magnetic defenses, being guided directly towards the magnetic poles where they can interact with our atmosphere. Upon entering the upper atmosphere, these high-energy electrons and protons collide with atoms and molecules of atmospheric gases, primarily oxygen and nitrogen. These collisions transfer energy, exciting the atmospheric particles to higher energy states. But these excited states are unstable. Almost immediately, the energized atoms and molecules release this excess energy by emitting photons of light. This process is very similar to how a neon sign works, where electricity excites gas to produce light. This light is what we perceive as the aurora. The altitude at which these collisions occur and the type of gas involved determines the color of the aurora. Different atmospheric molecules are concentrated at different altitudes and emit light at specific wavelengths when energized, creating a vibrant palette in the sky. The most common and iconic auroral color is green, typically appearing at altitudes between 100 to 300 kilometers. This vibrant hue results from energetic electrons colliding with atomic oxygen, producing its characteristic emerald glow due to the emission line in the green spectrum. Red auroras, while less common, are also produced by atomic oxygen, but at much higher altitudes, often above 300 kilometers, extending up to around 400 kilometers. Here, the oxygen atoms are sparser, leading to slower de-excitation processes and emissions in the red part of the spectrum. Nitrogen molecules and ions contribute the blue and purple hues, typically appearing at lower altitudes, below 100 kilometers. Blue light specifically comes from ionized nitrogen molecules that have regained an electron, while purple and pink shades arise from excited nitrogen atoms. Less frequently, pink and white auroras can be observed. Pink is often a blend of red from oxygen and blue from nitrogen, particularly when auroras extend to lower altitudes. White can be an illusion, a very bright aurora appearing colorless to the human eye due to its intensity. Auroras are not static. They are highly dynamic phenomena, constantly shifting, swirling, and pulsating. These movements are influenced by the ever-changing conditions of the solar wind and the complex interactions within Earth's magnetosphere, creating a living light display. The shape of the aurora, often a curtain-like structure, is a direct result of how the magnetic field lines guide the charged particles. The particles precipitate along these lines, forming elongated emissions that appear as shimmering draperies or rayed arcs across the sky. Scientists categorize Earth's auroras into several types based on their appearance and behavior. Discrete auroras are the most familiar kind, characterized by bright, distinct arcs, rays, and folds, often moving rapidly and intensely in the night sky. Diffuse auroras, on the other hand, are fainter and more uniform, appearing as a broad, unstructured glow that can cover wide areas of the sky. These are caused by a different kind of particle precipitation, often less intense and more widespread than discrete events. Pulsating auroras appear as patches that repeatedly brighten and dim, often with a period of several seconds. This rhythmic behavior is still an active area of research, believed to be linked to waves within the magnetosphere modulating particle precipitation. Even more exotic types exist, like black auroras, which are actually regions of asterisk-reduced emission within active auroras, appearing as dark voids. They are caused by regions where magnetic field lines allow fewer particles to reach the atmosphere. Auroras occur predominantly within the auroral oval, a ring-shaped region centered around Earth's magnetic poles. This oval constantly shifts in size and position depending on the intensity of the solar wind and geomagnetic activity. The strength of an aurora is directly tied to solar activity. Powerful solar flares and coronal mass ejections, or CMEs, release massive bursts of plasma and magnetic fields into space. When these directly impact Earth's magnetosphere, they can trigger spectacular auroral displays. A geomagnetic storm occurs when a strong solar wind disturbance significantly reconfigures Earth's magnetosphere. These storms can intensify auroras, causing them to expand away from the poles and become visible at much lower latitudes than usual. While beautiful, powerful geomagnetic storms can have practical consequences, they can disrupt satellite communications, GPS systems, power grids, and even pose radiation hazards to astronauts in orbit due to the increased particle flux. Scientific monitoring of auroras and solar activity is crucial. Satellites like NOAA's GOES series and NASA's ACE and DSCOVR missions constantly observe the solar wind and magnetosphere, providing vital data for space, weather predictions, and aurora forecasts. Ground-based observatories also play a vital role. All-sky cameras capture wide-angle views of auroral displays, while spectrographs analyze the light to understand the atomic processes occurring at different altitudes, helping refine our understanding of atmospheric composition. The study of Earth's auroras has provided fundamental insights into plasma physics, atmospheric chemistry, and the complex interactions between celestial bodies and their star. These phenomena are direct manifestations of the fundamental forces at play in our solar system. Yet Earth is not unique in hosting these spectacular light shows. As we venture further into the solar system, we discover that auroras are a common feature on planets and even some moons, each with its own unique characteristics and scientific mysteries. The gas giants, with their massive sizes and incredibly strong magnetic fields, host the most powerful and exotic auroras in our solar system. Jupiter, the largest planet, presents a truly spectacular and unique auroral display, vastly different from Earth's. Jupiter's magnetic field is the strongest of any planet in our solar system, roughly 20,000 times more powerful than Earth's. This immense magnetosphere captures a vast amount of charged particles, creating a truly immense environment for auroras. Unlike Earth's auroras, which are primarily driven by the solar wind, Jupiter's auroras derive significant energy from the planet's rapid rotation. Jupiter spins so fast that its magnetosphere drags charged particles around with it. This rapid rotation creates an enormous electric field that accelerates particles towards the planet's poles. This internal generation mechanism means Jupiter's auroras are almost constant, never truly disappearing, unlike Earth's, which depend on solar events. Furthermore, Jupiter's volcanic moon Io plays a crucial role in its auroral displays. Io, being the most volcanically active body in the solar system, constantly spews tons of sulfur and oxygen into space, forming a plasma torus around Jupiter. As Jupiter rotates, it sweeps through this plasma torus, further accelerating the particles within it. These ionized particles are then channeled down the magnetic field lines to collide with Jupiter's atmosphere, creating a distinct auroral footprint from Io. Jupiter's atmosphere is primarily composed of hydrogen and helium, with trace amounts of methane, ammonia, and water. When these gases are excited by incoming particles, they emit light primarily in ultraviolet, UV, and infrared wavelengths, mostly invisible to the human eye. Observations from the Hubble Space Telescope have been crucial for studying Jupiter's UV auroras. These images reveal dynamic, complex structures, including a main auroral oval and distinct spots that are the footprints of Jupiter's largest moons. The Juno spacecraft, currently orbiting Jupiter, provides unprecedented close-up views of its auroras. Juno's instruments detect both UV and X-ray auroras, offering new insights into the high-energy processes occurring in Jupiter's polar regions. Jupiter even has X-ray auroras, first detected by the Chandra X-ray Observatory. These energetic emissions are likely produced when highly charged ions, like oxygen and sulfur ions, accelerate down Jupiter's magnetic field lines and collide with its atmosphere. The mechanism for X-ray auroras involves charge exchange, where a fast-moving, highly charged ion captures an electron from a neutral atom in Jupiter's atmosphere, then subsequently emits an X-ray photon as it de-excites. Saturn, the ringed jewel of our solar system, also boasts magnificent auroral displays, though they share characteristics with both Earth and Jupiter. Like Jupiter, Saturn possesses a powerful magnetic field, second only to Jupiter's in strength. Saturn's auroras are driven by a combination of solar wind activity and the planet's internal plasma generation. While not as dominant as Jupiter's rotational influence, Saturn's rapid spin does contribute significantly to its auroral dynamics. Observations from the Cassini spacecraft revealed a strong correlation between Saturn's auroras and the solar wind pressure. When the solar wind intensified, Saturn's auroral ovals brightened and expanded, much like Earth's. Saturn's auroras also appear primarily in the ultraviolet, due to its hydrogen-rich atmosphere. However, Cassini also detected infrared emissions, revealing different depths of penetration by the charged particles into Saturn's atmosphere. A peculiar feature spotted by Cassini was a series of bright, transient auroral curtains radiating outwards from Saturn's main auroral oval. These are thought to be caused by sporadic magnetic reconnection events closer to the planet. Saturn's auroras exhibit complex dynamics and variability, including auroral storms that can last for several days, indicating prolonged periods of intense energy input into the magnetosphere, likely from extended solar wind disturbances. Saturn's unique ring system subtly interacts with its magnetosphere, potentially influencing the trajectories of some charged particles and contributing to subtle auroral features near the ring plane, though this effect is generally minor compared to solar wind. The gas and ice giants Uranus and Neptune represent another class of auroral displays. Due to their extreme tilt, the magnetic poles of Uranus are dramatically offset from its rotational poles, creating highly unusual auroral patterns. Uranus's magnetic field is exceptionally complex, often described as highly non-dipolar, meaning it does not resemble a simple bar magnet. This convoluted field geometry leads to auroras that are not centered on the geographic poles and can be quite chaotic. Observations from the Hubble Space Telescope have shown Uranus's auroras as small, bright, and highly variable spots of ultraviolet light at various longitudes, rather than a continuous oval, reflecting the planet's unique magnetic configuration. Neptune, similar to Uranus, also has a magnetic field highly tilted and offset from its rotational axis, leading to similarly complex and transient auroral displays. These ice giants' deep, methane-rich atmospheres filter visible light strongly. Both Uranus and Neptune's auroras are thought to be influenced by a combination of solar wind and internal processes, but the details are less understood than for Jupiter or Saturn, partly due to fewer spacecraft missions. The main atmospheric constituents of Uranus and Neptune are hydrogen, helium, and a significant amount of methane, which absorbs red light strongly. This means their auroras primarily emit in the infrared and ultraviolet ranges. Moving beyond the gas and ice giants, the terrestrial planets present a different set of challenges and auroral mechanisms. Mars, our red neighbor, lacks a global magnetic field, but still exhibits auroral phenomena. Billions of years ago, Mars likely had a global magnetic field. Today, only localized regions of remnant magnetism, known as crustal magnetic fields, persist in its ancient southern highlands. These are like scattered patches of weak magnets. When the solar wind directly interacts with these crustal magnetic anomalies, it can create localized, patchy auroras, distinct from the polar ovals seen on Earth or the gas giants. These Martian auroras are generally much fainter and smaller. Discovered by the European Space Agency's Mars Express orbiter, these ultraviolet auroras appear over regions of strongest crustal fields, particularly during periods of intense solar activity when the solar wind is unusually strong. NASA's MAVEN, Mars Atmosphere and Volatile Evolution, mission has provided extensive data on Martian auroras. MAVEN confirmed that these auroras are caused by directly incoming solar energetic particles interacting with the planet's upper atmosphere. Unlike Earth, where particles are guided by a global field, on Mars, solar wind particles can directly reach the upper atmosphere, exciting carbon dioxide, oxygen, and hydrogen atoms to produce mostly ultraviolet and some visible green light. Mars occasionally experiences another type of diffuse aurora, known as a proton aurora. This occurs when high-energy protons from the solar wind exchange charge with hydrogen atoms in Mars's exosphere. These neutral hydrogen atoms then strike the upper atmosphere, fluorescing in ultraviolet light. This can create a global, albeit very faint, invisible glow around the sunlit side of Mars, not requiring crustal fields. Venus, our scorching hot neighbor, also lacks a global magnetic field. Instead, the solar wind directly interacts with its upper atmosphere, creating an induced magnetosphere that deflects some of the solar wind, but also causes auroras. Venus's auroras are primarily caused by the direct impact of energetic electrons from the solar wind into its upper atmosphere, which is predominantly carbon dioxide. This excitation causes the carbon dioxide molecules to glow. These auroras are typically very diffuse and widespread, covering much of the planet's night side. Unlike Earth's concentrated polar displays, Venus's auroras are not confined to specific magnetic poles due to the absence of a global field. Observations from the Venus Express spacecraft confirmed that these auroras are mostly in the ultraviolet range, although some faint visible green light has been detected. The intensity varies significantly with solar wind conditions. The mechanism on Venus is different from magnetized planets. Solar wind particles plunge closer to the atmosphere, directly interacting with atmospheric particles to create emissions, rather than being guided by magnetic field lines. Beyond the planets, even some moons in the outer solar system display auroral phenomena. Jupiter's moon Ganymede, for instance, is unique because it's the only moon known to possess its own substantial magnetic field. Ganymede's intrinsic magnetosphere interacts with Jupiter's much larger magnetosphere, creating a complex magnetic environment around the Moon. This interaction is the primary driver of Ganymede's auroras. The charged particles from Jupiter's magnetosphere are funneled along Ganymede's magnetic field lines to its poles, causing its oxygen-rich thin atmosphere to glow in the ultraviolet. Hubble observations revealed two distinct auroral rings. Jupiter's moon Europa, though lacking an intrinsic magnetic field, also exhibits auroral emissions. These induced auroras arise from its interaction with Jupiter's powerful, rotating magnetic field. As Jupiter's magnetic field sweeps through Europa, it generates electric currents within the Moon's subsurface ocean. These currents create an induced magnetic field, which then interacts with Jupiter's field to accelerate particles into Europa's thin atmosphere. These auroras on Europa are also detected in UV wavelengths and are thought to originate from oxygen molecules on or near its surface, excited by the particle bombardment unique to its interaction with Jupiter's plasma environment. Saturn's moon Enceladus, known for its powerful geysers of water vapor, also participates in auroral processes. As Enceladus ejects water into space, this forms a plasma torus around Saturn, much like Io at Jupiter. The interaction of Saturn's magnetosphere with this water-rich plasma, combined with direct electron bombardment of Enceladus's thin atmosphere, is believed to cause auroral emissions detected by Cassini's instruments. These auroras on Enceladus, generally faint and primarily in the ultraviolet, provide clues about the composition of its plumes and the dynamics of its interaction with Saturn's magnetosphere, making it a target for future study. The study of planetary auroras is fundamental to understanding space weather throughout the solar system. By observing these light shows, scientists can infer the strength and configuration of planetary magnetic fields, even from great distances. Auroras act as powerful remote sensing tools. The color and intensity of the light provide information about the atmospheric composition and density of a planet, as different gases emit light at specific wavelengths when excited. By tracking the movement and changes in auroral ovals and patterns, researchers can deduce the strength and direction of solar wind surges and how a magnetosphere responds to these dynamic external pressures. The insights gained from studying auroras on other planets help us understand the potential for life beyond Earth. A strong, protective magnetosphere, indicated by robust auroras, is crucial for preserving an atmosphere and shielding a planet from harmful radiation. Planets lacking global magnetic fields, like Mars and Venus, demonstrate how atmospheres can be eroded over geological timescales by the direct impact of the solar wind, stripped away into space, showing auroras are indicators of atmospheric loss. Therefore, the presence and characteristics of auroras on exoplanets could become a critical parameter for identifying potentially habitable worlds. Robust auroral activity might suggest a long-lived atmosphere. Future telescopes, like the James Webb Space Telescope, are starting to offer new capabilities for observing planetary atmospheres and indirectly inferring aspects of their magnetic fields, bringing us closer to discovering exoplanet auroras. Detecting auroras on distant exoplanets will be incredibly challenging, requiring sensitive instruments and innovative techniques. Such observations would provide direct evidence of an exoplanet's magnetic field and atmospheric composition. One promising method involves looking for radio emissions. Just as here in our solar system, powerfully magnetized planets like Jupiter emit radio waves during auroral processes, which could be detectable from vast distances. The study of planetary auroras is a vibrant and ongoing field of research. Each new mission, each new observation adds another piece to the complex puzzle of planetary magnetospheres, atmospheres, and their evolution. Unraveling the mysteries of these celestial light shows deepens our understanding of the fundamental physics governing our universe. From the elegant dance in Earth's skies to the powerful, invisible glows on the gas giants, auroras are truly cosmic messengers. Earth's auroral oval is not perfectly circular. It is slightly displaced towards the night side, known as the harangue discontinuity, due to the complex interaction between the solar wind and the magnetosphere's tail. During intense geomagnetic storms, the oval can expand significantly, reaching lower latitudes and even splitting into multiple rings or double ovals. A rare but spectacular phenomenon caused by sustained, extreme pressure on the magnetosphere. Sometimes very high-altitude, stable auroral red arcs, SAR arcs, can appear. These are not caused by direct particle precipitation, but by heat energy from the magnetosphere transferring to atmospheric oxygen, causing it to glow red. Proton auroras, caused by energetic protons from the solar wind impacting the atmosphere, are typically diffuse and less visually striking than electron auroras. They are often indistinguishable to the naked eye, even though they constantly occur. The substorm is a fundamental process in Earth's magnetosphere that releases accumulated solar wind energy, powering many discrete auroras. It involves the sudden reconnection of magnetic field lines in the magnetotail. This reconnection event accelerates a huge burst of particles towards Earth, leading to a dramatic brightening and expansion of the auroral oval, usually starting near midnight local time within the oval. The northern and southern auroras are typically mirror images of each other, reflecting the conjugacy of Earth's magnetic field lines. When a solar event impacts one pole, a similar display usually occurs simultaneously at the other. Scientists also study electromagnetic, Whistler waves, and chorus emissions within the magnetosphere. These waves can interact with charged particles, scattering them into the atmosphere and contributing to pulsating and diffuse auroras. The historical record of auroral sightings, documented in ancient texts and cultural artifacts, provides valuable proxy data for solar activity levels long before modern instrumentation, helping to reconstruct past solar cycles. Jupiter's main auroral oval is relatively stable, but within it, highly dynamic and transient features appear, often attributed to the interaction between the planet's strong magnetic field and variations in the plasma torus. The footprints of Jupiter's moons Europa and Ganymede within its auroras are particularly fascinating. These suggest complex electrodynamic coupling between the moons and the giant planet's magnetosphere, acting like generators. These moon footprints are caused by Ulfen waves, electromagnetic disturbances that travel along magnetic field lines between Jupiter and its moons. As these waves reach Jupiter's atmosphere, they accelerate charged particles to create the auroras. Saturn's auroras can also exhibit X-ray flares, brief bursts of X-ray emissions often associated with the main auroral oval. These are thought to be caused by highly energetic particle precipitation during magnetic reconnection events. The auroral beads phenomenon on Saturn, short-lived bright spots forming a string around the auroral oval, offers clues about small-scale magnetic field instabilities and localized particle acceleration processes. Cassini also detected a polar hexagon in Saturn's atmosphere, but this is a weather phenomenon, a vast hexagonal cloud pattern distinct from the aurora, although the aurora often lies directly within its boundaries. On Uranus, the Voyager 2 flyby revealed only weak, sporadic auroras due to the then-quiet solar conditions. Later Hubble observations during more active solar periods showed brighter and more frequent displays. The highly tilted and offset magnetic fields of Uranus and Neptune result in auroral activity that is often not symmetrically distributed around their rotational poles. This asymmetry distinguishes them from Earth, Jupiter, and Saturn. The unique magnetic field geometries of Uranus and Neptune may also lead to auroras forming over a broader range of latitudes rather than tightly confined ovals. Although intense, continuous observations are needed to confirm this. Martian auroras, sometimes called discrete auroras due to their localized nature, are best seen on Mars's night side when direct sunlight doesn't overwhelm the faint glow, often around 130 km altitude. The MAVEN mission at Mars has also discovered diffuse auroras on the dayside, caused by scattered solar wind electrons, invisible to the eye but detectable by instruments, showing a more global interaction than the localized nightside ones. Even though Venus lacks a global magnetic field, it has a magnetic obstacle created by the solar wind pushing against its ionosphere. This forms a bow shock and magnetosheath that influence particle entry. The nightside aurora on Venus is most prominent around the terminator line, the boundary between day and night, where the induced magnetic field lines can funnel some particles into the atmosphere. The study of Venus's auroras provides a natural laboratory for understanding how charged particles interact with unmagnetized planetary atmospheres, offering valuable comparisons for exoplanets lacking protective fields. The detection of auroras on Ganymede was a significant discovery because it confirmed the presence of an intrinsic magnetic field generated by a liquid core, making it unique among solar system moons. The Hubble Space Telescope detected Ganymede's auroral emissions in ultraviolet light by looking for specific oxygen lines. The distinct wobble of its aurora indicated the presence of the Moon's own magnetic field. The Galileo spacecraft helped confirm Europa's induced magnetic field by directly measuring a localized magnetic signature. This provided indirect evidence for the existence of its subsurface ocean, influencing its auroras. While less visually spectacular than the gas giants, the auroral activity on icy moons like Europa and Enceladus is crucial for understanding the processes that energize their tenuous atmospheres and potentially affect their subsurface oceans. The concept of reconnection is crucial for many auroral processes. This is when oppositely directed magnetic field lines merge and suddenly snap, releasing enormous amounts of energy that accelerate particles and cause bright auroras. This magnetic reconnection plays a key role in Earth's substorms, driving the most intense auroral displays. It's a universal process occurring across cosmic plasmas, not just in planetary magnetospheres. Solar Cycle 25, currently underway, promises increasing solar activity in the coming years. This heightened activity is expected to bring more frequent and potentially more intense auroral displays for Earth observers. Citizen science projects like Aurorasaurus allow the public to report aurora sightings. This crowdsourced data helps scientists track auroral behavior over vast geographical areas, complementing satellite and observatory data. The aesthetic appeal of auroras draws millions of tourists to polar regions each year, fostering appreciation for natural wonders and indirectly supporting scientific research through increased public awareness and funding. Beyond beauty, auroras underscore the fragile balance of a planetary environment. They are constantly reminding us of the powerful, invisible forces from our star and from within a planet that shape its habitability. The ongoing search for exoplanet auroras might one day lead to the discovery of worlds with conditions similar to early Earth, providing crucial insights into how life might have emerged and thrived under ancient auroral skies. Future missions, like the European Space Agency's JUICE, Jupiter Icy Moons Explorer, and NASA's Europa Clipper, will further explore the Moon interactions with Jupiter's magnetic field, revealing more about their unique auroras. The comparative study of auroras across our solar system is a powerful testament to the diversity of planetary environments and the universal physical laws that govern them. Each world adds a unique chapter to the story of light in the cosmos. From the familiar green glow of our home planet to the invisible X-ray bursts on gas giants, planetary auroras are indeed lights beyond Earth, revealing the hidden dance between stars and the worlds that orbit them.